Okay, hey everyone. So we're going to be going over 14.3 problem 1. So this is a long problem, so I'm going to be going back and forth between each part for the question and the solution. So our question is going to be: a soldier can hide in one of the 5 foxholes, 1, 2, 3, 4, or 5. And a gunner has a single shot and may fire at any of the 4 spots A, B, C, or D. So a shot will kill a soldier if the soldier is in a foxhole adjacent to the spot where the shot was fired. For example, a shot fired at spot B will kill the soldier if he is in foxhole 2 or 3, while a shot fired at spot D will kill the soldier if he is in foxhole 4 or 5. Suppose the gunner receives a reward of 1 if the soldier is killed and a reward of 0 if the soldier survives the shot. So for part A, we're going to construct the reward matrix. So right here, since there are only 2 possible rewards, 0 and 1, this is what the reward matrix is going to look like for the gunner. Okay, so for part B, we're going to find and eliminate all dominated strategies. So we can observe that strategies and try to see if there are some better than others. And since a strategy is dominated if and only if it is worse or equal than another for any choice of the opponent's strategies, we can see that for the gunner there is not such spot. However, if we observe the soldier, we can see that column 2 is dominated by column 1, since it brings a smaller reward for the gunner's choice of row 2 and equal reward for all other choices. The same thing is with column 4 and column, which is dominated by column 5. So if we go to part C, the question is, we are given that an optimal strategy for the soldier is to hide 1/3 of the time in foxholes 1, 3, and 5. We are also told that for the gunner, an optimal strategy is to shoot 1/3 of the time at A, 1/3 of the time at D, and 1/3 of the time at B or C. So now you must determine the value of the game to the gunner. So for part C, these optimal strategies are obviously mixed strategies. So what we want to do is denote the mixed strategies as usual. So we're going to define them to these variables, x1 being the probability that a gunner shoots at A, x2 is the probability that gunner shoots at B, and then so on with x3 and x4, that being x3 is the probability that gunner shoots at C, and x4 is the probability that gunner shoots at D. On the other hand, y1 is going to be the probability that soldier hides at 1, y2 is the probability that soldier hides at 3, and y3 is the probability that soldier hides at 5. So using this information, we can see that x1 equals 1/3, x4 equals 1/3, and x2 plus x3 equals 1/3 as well. As for the y's, we have y1, y2, and y3 all equaling 1/3. So since the reduced reward matrix then would look like this, we can substitute the given optimal strategy values and calculate the expected reward for each player. Here we are only interested in the gunner's reward, and against soldier's strategy 1, the expected reward for the gunner is going to equal to 1/3. See the math right here. So against soldier strategy 3, the expected reward for the gamer is also going to be 1/3. Since we don't know x2 and x3, we must make such transformation so that we are left with the sum, which is known as against soldier strategy 5, the gunner's expected reward is going to also equal 1/3. As we can see, the expected reward in all cases is equal to 1/3. That's our answer. So moving on to part D, suppose the soldier chooses the following non-optimal strategy. Half the time, hide in foxhole 1, 1/4 of the time, hide in foxhole 3, and 1/4 of the time, hide in foxhole 5. Find a strategy for the gunner that ensures that his expected reward will exceed the value of the game. So, go down to our solution for D. So now we can observe the non-optimal strategy with values y1 equals 1/2, y2 equals 1/4, and y3 equals 1/4. So our goal is to select a strategy for the gunner so that the expected reward for him exceeds the value of 1/3 established with the optimal strategy. Since the soldier will hide at foxhole 1 half the time with probability 0.5 and the value by itself is greater than 1/3, we can choose the following strategy. Gunner only fires at spot A. That way we have that x1 equals 1, x2 equals x3 equals x4 equals 0. And the expected reward will equal 1/2, which is greater than 1/3, and that's the value of the game. So moving on to part E. So part E is just write down each player's LP and verify that the strategies given in part C are optimal strategies. Okay. So part E will observe the row player first and let his inform his LP. So denote his strategy as X1, 2, and 3. We can now observe the expected reward to the gunner against each of these soldier strategies. So against soldier strategy 1, the expected reward is X1. Against strategy 2, the expected reward is X1 plus X2. Against strategy 3 is going to be X2 plus X3. Against strategy 4 is X3 plus X4. And strategy 5, the expected reward is just going to be X4. They are equal. So by the assumption, the soldier will choose a strategy that makes the gunner's expected reward equal to the minimum of X1, X1 plus 2, X2 plus 3, X3 plus 4, and X4. So knowing this, the gunner should choose X1, X2, and X3 to make this minimum as large as possible. Now we have the LP being the max equals V, and we're going to have these for our LP. So on the other hand, the LP for the soldier is going to be formed using this logic, but this time we're going to denote his strategies as Y1, 2, 3, 4, and 5. So we can observe the expected reward to the soldier against each of the gunner strategy. So against the gunner strategy A, the expected reward would be X1 plus X2. Strategy B would be X2 plus X3. Against strategy C, the gunner's expected reward is X3 plus X4. And against gunner strategy D, the expected reward to the gunner is Y4 plus Y5. So the gunner seems to know Y1 through Y5, and so he will choose a strategy that ensures that he obtains an expected reward of max Y1 plus 2, Y2 plus 3, Y3 plus 4, Y4 plus 5. Hence, the soldier should choose Y1 through Y5 to make this maximum as small as possible. Another thing that we must incorporate in order for this to be a mixed strategy is that the sum of those probabilities must equal 1, and they must be non-negative. So therefore our LP is this.